So all of this is just an introduction. So those that are joining online, they haven't missed too much. I just was presenting what we do as an institute, then my group, and now I will zoom in the topic of this session that is very narrow now, but I would like to start with wood and how wood and water really love each other, and how, if we understand those interactions, then we can create materials, right? And one thing that is shocking for me to learn, and that was actually 2 years ago, this publication from Nature, very, very telling. This is in close to Zambia, the evidence for the earliest use of wood in an structural form, structural materials. And that dates back to almost 500,000 years ago. So since then, we have been using wood. So wood really comes with civilization, and it's so important. And as you also recognize, wood has become really a very exotic, very sexy material nowadays. So those of you who are working with wood, I would say, okay, this is an amazing topic for doing research. And I want to illustrate that message with a little experience that I had when I went to my home country, Venezuela. I was born in Venezuela, and I haven't been there in a long time. But 4 years ago, I came for a visit, and then I went to my hometown, and then I found a museum toy museum with a fellow, last name Calderon, who has an absolutely one of the best collections of toys. And he also has been recording the history of toys. And I learned from that visit that toys more or less follow similar evolution. We're starting to work with toys made out of wood, celluloid to tin to plastics, and now back to wood. Wood has becoming very trendy in the area of toys. So to me, that means back to the future, and that's why I put on the right the back to the future idea, because now we think about wood for construction as a very good way to solve many issues. It's absolutely an amazing material. But wood is not only wood, but the constituents that we have in wood. And this illustration you perhaps have seen many times in one way or the other is the fact that in wood we have a multi-scale hierarchical arrangement of polymeric materials, biopolymers that include, as you know well, cellulose, lignin, hemicelluloses, as well as different polyphenolic compounds and extractives. And that hierarchy is shown here as you go around the circle, right? Between wood, the cell wall of fibers, and the fibers that are in the cell wall, and the more nanoscale materials that you can extract from that beautiful hierarchical structure. But that doesn't only applies to wood. There are a number of other materials that we have used in our lab. They are shown here that have also such quality, right? And that goes from coir fibers, from coconut shell to pineapple leaves, or to agave in Mexico, to bamboo, and many others. So there are common structuring of those biopolymers in different sources that go beyond plants, by the way. It goes to animals and also algal resources that contain cellulose. And the point here is that when we want to deconstruct wood or fibers into smaller units, then we had to put some mechanical, chemical, or biological energy to reduce the size, to open up that structure, and then we go from top down, from the fiber level to the microcellulose, nanocelluloses, cellulose nanocrystals. And when we go to the molecular level, we are talking about cellulose solutions, right? So for me, cellulose is a polymer, but more than a polymer, as you can see here, a linear polymer, a linear homopolymer. The beauty of cellulose is the structure it forms. It's when cellulose molecules find each other in the process of biosynthesis, in a co-crystallization process, those cellulose chains form structures that are absolutely beautiful, right? And of course, that's a quite interesting topic that is of how using sunlight, CO2, and water, nature creates these beautiful structures. So that's what we do. In some cases, we deconstruct wood into smaller units, and then we put them back together to create materials, right? And that can be wood for construction in buildings, but could also be for replacement for plastics, or it can be also energy materials, electronic materials, biomedical materials. And that now is a bottom-up process where we put things, the building block, back together, right? But in a pre-designed manner. But what I want to reflect with you is that that process happens because first, those materials that we deconstruct and we obtain from nature are in contact with water and form what we call a hydrogel. So a high viscosity material that feels like a gel, and if it is with water, we call hydrogel. So those materials bind to water very strongly, they hydrate and form hydrogels, and the magic happens when we start to work with those hydrogels and we remove water. So we add water and then we remove water. And in removing water, we create materials. So there is something to the hydration and dehydration that is the secret for the production of advanced materials out of fibers. That's how I see this. And the best example to illustrate this process of adding water to then take it away is paper making. So some of you have training in paper making, and you will recognize that in paper making, we take wood fibers, we put them in a suspension in water, we drain that water, then we dry, and then we get paper. And paper becomes a two-dimensional structure that came from the tree that is a circular cross-section material, right? So we go from wood to two-dimensional paper, and paper as a material is very unique. If you think about the mechanical properties and all the properties that paper has that allow us to use it in so many different things for already 2,000 years, right? No replacement for paper. But the secret is, again, more specifically to the generic idea that I presented previously, is that we here add water and then remove water. And that applies not only to fibers in paper making, that would be this one here, that also applies to wood, and that applies also to nanoscale materials like the ones that I have introduced. So I will try to start here in this talk. I will start to wood, how this concept applies to wood, to fibers, and if I have time, we started today a little bit late, but if we have time, I would like to also look into nanoscale materials, right? How we play the same idea with these materials. And to do that, I want to reconnect with my initial, steps as a PhD student. I graduated in 1998, so it was quite a long time. And the main topic of my interest was how the surface of cellulose, let's say fibers, look like at the nano scale. And there was already some information available that on the surface, cellulose looks like eelgrass on the bottom of a pond, but there was no proof to this. Then my former advisor looked into this with collaboration with Sweden, and at a very small scale, they observe those dangling tails of cellulose. So in the presence of water, the surface of the fibers will look like this. It's not something that is just flat. There is something. And these are highly hydrated chains of cellulose, not a single molecule of cellulose, but chains of cellulose forming fibrils that feel like a polyelectrolyte, like a polymer that is charged, highly hydrated, and is coming out from the surface. Beautiful, because that also explains the adhesion between fibers in paper-making process. So these materials have to be active in that process. And in fact, this is what I can say, that in aqueous media now, moving forward with the idea, in aqueous media, there is a number of interactions. You can read those in this blue block panel that really allows for the materials to interact with each other and form structures that are very strong, that bond with each other and very strong. And all of this depends on a number of factors that relate to the medium, pH, temperature, salts, ionic strength, type of salts, these are all will affect the interaction. That is the hydration and how when a surface like this connects with another surface and makes a structure like paper, right? So it's beautiful topic from the point of view of the science. Let me see how this can be translated now moving forward 20 years after now to wood, because what I just explained to fibers about fibers also apply, I promise you, to wood. So this is a little bit more recent in a paper a few years ago, where we look into utilizing wood losses and waste. And here the observation was that at least in the Vancouver city, there is a lot of waste that goes to landfill that is coming from construction and demolition. That's wood from those activities. Also commercial and residential waste. If you think about the US, that construction and demolition waste that is essentially wood is very underutilized. And in many centers, cities, municipalities, there is a huge interest in recycling wood. And of course, we started to connect this with paper making. But the situation today is that very little is recycled as far as wood, and most of the wood will go to landfill. But in an effort to have a more circular bioeconomy, of course, this has to be an option. And in many of our proposals that we are now currently very active, we really are putting this on the top level. Not only wood waste, but also food losses and waste that can be utilized. Agricultural waste. So in my humble opinion, I think we need to look pretty much into the utilization of those materials that are underutilized. From the point of view of wood, there is, of course, a good reason to do this, because nowadays, wood for construction, for buildings, multi-story buildings have become very topical, right? That's very, very important. And this is the building that was built in our university in UBC. It's an 18-floor building that is all wood, except some components that are cement, where the elevators goes. But essentially, it's a fully wood built. And it's amazing because that means that we're storing carbon there for a long time, long-lived carbon, and then can be recycled. If we think about this construction as a number of years, it depends, 50, 100 years, 400 years, or if you go to the pagodas in Japan, maybe more than 500 years. Wood can be quite resistant to many factors, and you can use it for a long time. But the idea here is to prolong that life, to extend the life of wood by recycling. And that's important then for us to consider, because what we consider a waste can be really important feedstock for what we do. And what we have here is we tested decayed wood, sawdust, or what I have already introduced, and thought, okay, how can we use this hydration, gelation, and regeneration at the interface to put things together, back together. So the basic idea here, well, there is a cost. There is a chemical cost doing this. The first step here was removing lignin. So that can be utilized too. Remove lignin, delignify the wood pieces that are there. And we do partial dissolution of the cellulosic component that is left in the wood material. We're not dissolving the whole wood. We're only dissolving the very top interface or layer of wood. And then by putting this material in water, what you're going to achieve is these cellulose chains that I described earlier are going to be there in green color, will be highly hydrated. And in a process that is called regeneration, followed by densification, they will start to bond the pieces together. So it's a form to glue pieces of wood back into a material that contains the same components initially. It's the same cellulose that existed in wood, just that we dissolve that cellulose that is only on the surface. We hydrate it, produce a hydrogel, and then by removing water, then that drying really brings pieces together by capillary forces, and then you have the establishment of a very strong bonding. So we go back to a monolithic material, but in this case, very strong. And what we found is that material actually achieve quite remarkable specific strength per unit density. That would be what we call at that time heel wood, here in red, compared to other materials that, again, per unit density, outcompetes many engineered materials. So it was a very simple idea, concept that takes from the paper making explanation that I gave earlier. Very simple. And that works. More recent work actually have gone in a different direction, is that we can reinforce the interfaces by doing the same that I showed earlier, but in this case, putting cellulose in the middle, and that cellulose can be paper. We dissolve that paper. You can use different solvents. They can be deep eutetic solvents, ionic liquids. There are many solvents that are capable of doing this. Having them, that cellulose hydrated and allowing for water to do its work, and then by removing water, dehydration, then bringing the pieces together. So it's an iteration, a different way to do what we showed earlier, but in this case, we supplement the material with cellulose, okay, to reinforce this. And now there are a few papers already out by us and collaborators and colleagues that show that this is actually quite attractive. I don't say that this is a solution that is economical yet, but I think it's worth exploring because it's very simple. And of course, we have been looking into how this happens at the molecular level. So we're looking into a molecular dynamic simulation, coarse grain simulation, to look how the cellulose that is in the hydrated state, when water is removed, then achieves this very strong binding between the surfaces, right? So all goes down to cellulose. And the fact that cellulose as a homopolymer, linear polymer, highly hydrated, when you remove water, then you will have a strong bonding between the materials, including hydrogen bonding, van der Waals forces, and many other interactions. It works very well. And the materials that then you achieve are found to have very high shear strength or bond strength that quite remarkable values, both in plane and out of plane. So all to say that, and this, maybe you can think about this similar to the case of plastics. We always want for cellulose to behave like a plastic. That never will happen because plastics are plastics and cellulose fibers and paper, different things. So we need to think about them for what they are. And there are many great possibilities for cellulosic materials. But in the plastics, we talk about thermoplastics and thermosets, right? Thermosets. Thermosets are materials that you process by heating, and then you set the material, maybe cross-links, and then it's difficult to return the material to original state. It's set, thermosets. Well, in this field of bio-based materials, we talk about hydrosets. We don't use heat. We use water to set the material. And once we add water and remove water, the material is set. And that material that is set can be set in three-dimensional shapes that we can control. So think about thermosets and hydrosets. And this is what I illustrate here. Maybe you don't need to pay too much attention about the details here. But essentially, we really have the densification of the material in such a way that you produce those that you see on the far right. And at the end, if I have time, I show you what we're doing in this area to produce a leather-like material, but not using collagen or animal hides, but using veneer. Same idea. So hydroplasticization or hydroset as opposed to thermosets. Oh, here it is. So that's a concept also more recent. That was last year. We started to work in my research group with a designer, art and designer, together with the scientists to look into this. And what we did was to take veneer, pieces, flat pieces of, thin pieces of wood, and to play with concepts similar to what I have already indicated to you. Of course, there are more steps here. And what we get is a material that behaves like leather, but it's wood, but it's very flexible. And you can see on the far right that it feels not quite as a leather. I understand, because if you show this to any luxury brand and tell them this can be a substitute, they are not going to buy it. but nevertheless can be leathery enough not to be used in the things that we wear, but at least in sport goods, like in this case, a soccer ball. And the reason why we took this is, well, FIFA World Cup is coming this year, and that was a good concept. And that went all the way to the Expo 2025 in Osaka, where that was in an exhibition. So a little thing to also tell you that we should work also between scientists and artists, designers to communicate a message. And that's a message that is very strong, right? It's possible to use wood not only for construction, but in this case for leather-like materials. And in fact, now we have a project with a holding called Kering that is a matrix for Gucci, Saint Laurent, Balenciaga, and many luxurious brands looking into replacement of leather, because leather is one of the most terrible materials from the point of view of the sustainability and carbon footprint. So there is a need for that. Another example I'm giving here, I'm talking about wood. I think is the main subject for this community. But I want to further stress in a different line of work how beautiful wood is when it comes to other types of advanced materials. So this is work by my former PhD student and postdoc in Finland. And in this case, we took wood. We did like before. We removed some of the lignin. And then we decided to carbonize that wood that was absent of lignin. And then an observation took place. Is that the material, of course, becomes black. But if you look at the small scale features on the surface of those pieces of wood, what you can observe is a microarrays of fibrils that are exposed on the surface, right? With no intervention, they come up naturally, right, after carbonization. That's very nice because people design super black materials by growing carbon nanotubes vertically from a plane in clean rooms to produce highly engineered materials that are called super black. And super black materials are in high demand. There are materials that are super absorbent of light for thermal materials, for light absorption, and many other applications. Anyway, what the main idea that was triggered after this observation of vertically aligned carbon microarrays that are cellulose arrays, the same that we have been talking all along, the same that we put in the interface earlier, a bonding, but in this case in a different form. What these guys do is that because we have the lumen of the fibers in the wood structure, those microarrays can be very effective in, as I said, produce multi-scattering of light, and that means that light that comes in stays in by absorption and scattering. And that's what we found here. If you take a look at the total reflectance versus the light wavelength for typical non-engineered wood carbon, then this is the value, high reflectance. It's black, but not black enough. And we wanted to have something that really absorbs all light, nothing escapes. And then the value of that reflectance with this wood material that you see in the top right, in the black color here, is a material that is special. It's called super black. And super black exists. Is a material that is engineered. One of the applications that you will see in one of the examples is called the Vanta black. Vanta black is that if you have a coating with a material that is three-dimensional, you are not going to be able to distinguish the silhouette because all light is absorbed. So you cannot see anything. It's gone. This is very important in many uses, in military defense, in telescopes, but also in sunlight conversion to energy. You want to absorb all the energy, right? So here is an optical view of what also happens here. And these materials were found just by simple carbonization of wood. So we're not creating carbon nanotubes. We're not making any special engineered surface. We're just using wood. And that wood we found in a second follow-up article that was published that they weld optically. Like the same welding that we have been talking when we have two pieces of wood. Okay, here optically there is welding, meaning that if you take pieces of wood and you put them next together, after carbonization of the material, then you don't distinguish, you are not able to distinguish the interfaces. So it's very nice because now we can talk about high or large area construction materials. One application of this shown here earlier, much earlier, but with typical carbonized wood. This is not super black. Super black would be much more efficient. But in this earlier work where wood was carbonized, then it was possible to see how the material can be used in desalination and sunlight energy conversion, right? Because all the light is absorbed. This is heated locally, and then they can be used for that type of conversion. So very typical high-end material, but from the perspective of construction, you can realize that that can be used also in roof to produce quite interesting concept for cold areas, right? This is a picture that I took in a city called Porvoo, close to Helsinki, where I noticed that all houses have a black roof. And then I decided, okay, maybe this is a good example to show what we can do with this type of material, where you can really take advantage of the sunlight energy. Okay, that's the concept, very simple. So, check. So we talked so far about wood recycling. Now super black material, completely different topic, but all related together with surfaces, with the things that we're talking. Maybe I would like to give you another example of what is possible. In this case, achieving just the opposite, not to have a super absorber, but something that transmits all the light, transfers all the light. That is transparency and thermal insulation. And this is also important in construction because, as you can imagine, we have a lot of windows, and those windows really is where the energy is lost. Therefore, it would be ideal to have a window-like material that is transparent, but with good thermal insulation properties. And that's difficult, right? You have to have double windows and do, quite a lot to make sure that you have a low thermal transmission rate or a high barrier to heat. So here the idea is to produce transparent wood. This is a topic that is already well developed. Our colleagues in KTH, our colleagues in ETH and EMPA and others have worked on this. And also our colleagues in Maryland, now in Yale, have talked a lot about making wood transparent. But what we found here is maybe quite interesting because it's very simple and adds the thermal resistance that I already introduced. And the process here is very simple and follows the same lines that I have spoken so far. We take wood, we remove lignin, and then we do periodic oxidation of the material that is left. Here, essentially, what you have is replacement of OH groups by aldehyde groups. Those groups are reactive. They can find each other and cross-link. Then you get a material that can densify and become strongly bond together. So that's the whole thing. We use a little bit of chemistry and colloid science, surfaces, to then make a material that is transparent. So that's what we did here. And what I will show you next is how this operates. Very simple to follow. We take a wood. Here you have the density. So this piece of wood is a lot of air. You can grasp that from the density value that you see. In this case, it was a balsa wood. Of course, we always start with balsa. That is easy to operate. The cross-section and the plane view of the material, that would be the starting material. Then after delignification, of course, the density will increase. The cross-section signals the fact that the material becomes densified. But here the secret, once again, is in that process, what we did was to add water and remove water. And that remotion of water led to this process of densification. It's a drying-induced densification by something called capillary forces that we can maybe expand, but maybe we have no time now. But by capillary forces, surface tension forces, very high pressures will be applicable here, and the material will be densified. That's the lignification alone. But if we do the dialdehyde oxidation that I have introduced in the previous slide, what you will see is a further gain in density, and now you see that the material becomes transparent. That's because all the air is being expelled out. then the material bonds stronger. There is less solid air interfaces. That means less scatter of light, and that means light comes in and leaves the material. Transparency. Cross-section, plain view, gray material. And strong, dense, strong, and transparent. And then one additional permutation. Now we don't need to be restrained to one single piece. We can have a sort of a plywood type of a structure with 3 layers of these pieces of wood. The transparency will suffer a little bit, but as you can imagine, this material has much better mechanical properties, right? So here, transparent, low thermal conductivity, and very strong. In this case, multi-layering. Once again, the idea is the same that I showed at the very beginning in paper making. We add water, we remove water. That's it. So this is all what I have said is shown here in graphs. Light transparency. This is the densified wood. And then here we have the one that we produce by delignification and dialdehyde. So you can see the transmission is much larger. And then as far as the mechanical strength, here we have the initial piece of wood. On top, we have the 3 layers that are stuck together in a crisscross configuration. So very high strength. So very good values. So this material, interesting. Don't ask me about the cost because it's the principle, right? But we need to work on that. And then as far as the thermal resistance, then you can see here the thermal conductivity plot of glass versus this material, much less, right? So that's good, meaning that we have a glassy material that can be used, it's transparent, but also can be an insulator, right? As a concept, it works very well, and we play with a bunch of things to show that. Okay, maybe one more example of things that we can do with wood, just working at the interface, adding water and removing water. The last example, this morning I was discussing a lot of foams. There is a foam here that is very simple to make, and it's an interesting one that I propose to you. Same concept. We started with wood. We remove lignin, and the lignin can go to somebody else to work with the lignin. And then that piece of wood, then we can call hollow wood. In this particular case, we make sure that we preserve all the cellulose and the hemicelluloses. So this is a high yield material. We lose 30% of the material and by way of the lignin that is removed, but the remaining is structurally the same components, and they preserve the structure. Here we have then, after removal of lignin, the oxidation that I mentioned into aldehyde form, and then we follow with a reduction to make the aldehyde groups to be converted into alcohol groups. So to neutralize, to make the material less reactive. So the densification that we showed before is not going to happen here, just the opposite. So we transform the aldehyde groups into OH groups by reduction. The material then is no longer reactive, doesn't cross-link. It will lose mechanical strength, but it will gain in resiliency, because what you get at the end is a piece of wood that acts, looks, and behaves like a foam. And that's what you're seeing here. So it's a piece of wood that is a foam. It's not built from bottom. It's not built from bottom up. It's from top down. You do extraction, and that's it, and chemical modification. That piece of foam is also an isotropic. It is compressible in this direction, but it's not compressible in the opposite direction because you have the fibers and the lumen aligned in one direction, right? Not in the other. So for some applications, that can be quite interesting. So we had a conversation with Apple that came to visit our labs, and they found this quite interesting for packaging materials, right? For electronics and so on. Anyway, we have something that is fully compressible, biodegradable, and it's just cellulose and hemicellulose. If you do given modifications, then you can make also hydrophobic. This is highly hydrophilic. With chemical vapor deposition of silane, then you can make the material highly hydrophobic, and that's an example. Okay, talking about hydrophobic wood. This is my last example of wood, and yeah. So the idea here is, what if we don't remove the lignin? We keep the lignin. but we redistribute that lignin within the material. So this is the most recent step that the same student that made the foam now went over to continue this work in a different direction. What we did here was to take wood and dissolve in situ the lignin that exists in the cell wall and in the lamella of between the fibers, right? And we use a special solvent. And what we observe here is that the lignin is dissolved, but we didn't make any effort to extract that lignin. We keep that lignin. And the observation that was made almost by accident is that the lignin that is dissolved finds each other and clusters into particles when we remove the solvent, water. It clusters. Again, add water, remove water. And then those clusters of lignin also migrate from the inner parts of the cells to the outside. So you have migration of lignin to the surfaces, and we have clustering. You have two things, surface energy and topology. The two help to produce very high super hydrophobic materials. That's what I show here next. But essentially, that's what we have. We have upon regeneration by removal of the solvent and then drying, then it's possible to go from here to here. And what you notice here are a lot of lignin particles decorating the material. So we're not removing the lignin, we're keeping it. It's just restructuring the lignin. And by doing that, you notice we go from top down. We go from something that is more or less light to something that is darker because of the lignin goes to the surface. But also here you put a droplet of water and it will spread completely wet. Here it doesn't wet. That on itself is enough to say, okay, this is a very nice way to engineer wood to make it super hydrophobic. But the student, now a postdoc, went a step further. Realizing the hydrophobicity, super hydrophobicity of this wood piece, you can notice that when we put a droplet of water against the wood, it doesn't really interact at all. And that's what I introduced at the beginning. I'm very interested to look into the interactions, right? Between water, in this case, between water and wood. Super hydrophobic. And then the point here is, being in Vancouver where there is rain all the time, can we use this for, can we take advantage of this in combination with rain? You can read the details here. The fact is that if you have untreated wood, water will fall, will stick, right? Because wood is, unless it's treated, is quite wettable, right? But the treated wood that we did by this lignin relocation shows a different behavior because it's fully repellent to water, the water falls and then rolls, right? And this can be used not only to protect the house, but also to produce contact electrification. So this is a little fancy extra step where the sliding droplets locally generate charges, and that lead to something called charging. When you put things in contact, solids in contact, you generate electricity. If you rub materials, you produce electricity. But also that applies to solid liquid system. If droplet of water impact a solid, it will generate electricity as well. That can be recorded. If you put an electrode, it will be possible to measure that electrical generation. And that's what the student did here. It's difficult to see, but there are simulated rain falling on the pieces of wood with electrodes. And what she's recording here is the generation of electricity that can be used for something, right? Low energy. Anyway, this is now all people are publishing about this, very fancy, but the concept that really I want to maybe press on is the idea of the initial material that was transformed from simple wood to something that is super hydrophobic. Very simple. I don't think we have time. We started a little bit late, but I'm 5 minutes before half of the hour. I don't know if we leave the rest for questions.
Yeah, might be, but
Yeah. So I had more things here about fibers and then nanocellulose, but let's skip so that we can have some questions and answers, right? But very briefly, if you want to, I wanted to show very briefly Same concepts that I introduced for wood happen for cellulose fibers to produce materials by like mineralization or by 3D printing or wet spinning. All along is the same idea: add water, remove water, and you can travel around those quadrants where cellulosic fibers, in this case not wood, cellulosic fibers can be transformed and into products that are quite different. And you can travel in this diagram by playing with the forces. Add water and then remove water. That's the same concept for wood, applies also for fibers, and would apply also to nanocelluloses that I had at the very end. So with that, I finished. But let's go for the questions.
So very cool. And it's biodegradable. Is it compostable?
So all these pieces made out of wood, cellulose, lignin, because of the very nature, they are compostable. They will generate CO2 and, it will be fully biodegradable, compostable. No, that's the thing, right? We're not making the foam by adding components, right? We don't use fibers or lignin or other components to make a foam, building the foam bottom up. Here is just a subtractive effect. We take the wood as it is, we remove lignin, we chemically modify it, and that's it. And that will be to make the cellulose, to change the cellulose composition in such a way that we put first aldehyde and then OH groups. Very rich in OH groups. You will lose in mechanical strength, but you will gain in the resiliency and compressibility of that material, right? So no, we didn't play with that. We didn't add any special component. It's a subtractive process where we remove lignin and then modify chemically the fibers. Yeah, probably, yes. Now, the economy, I don't talk. The solvents that we use, I don't talk. That remains, these are just scientific, proof of concept ideas. But now we need to work on the scalability and, and we have been doing all of that, LCA and all of that, but it's still in progress. Yes.
I have a quick question. You said don't talk from economic aspect, but I was just wondering, it's very interesting what you presented, and what are the steps that require a lot of cost, and moving into the future, do you see any advancements in science that could help to reduce that?
That's where really it's so important to interface with people that know about economics, life cycle assessment. So that's what we're doing that I presented at a very early stage. Definitely. So where are the pinch points in those processes? Solvents. In many cases, we are using solvents that are not aqueous-based solvents, right? So some of those are pretty okay. The MSO, for instance, is one, not that we use here. But one that is coming very trendy and is very good is the case of ionic liquids. Ionic liquids are materials that in the past tended to be more related to high-cost solvents, but there is now enough progress that we can say new generation of ionic liquids are cheap and can be recycled. So in that process of recycling a solvent that is used, I think the economy will factor quite well because you recycle the solvent. So I would say deep eutectic solvents that I mentioned and ionic liquids that I also mentioned can be quite nice. The other solvent that we use in the one that I showed the quadrant, that was sodium hydroxide. Sodium hydroxide in water becomes a nice solvent for cellulose if you use low temperature. That's another example of a solvent that is low cost and can be quite useful, right? But in other examples that I show, we use more traditional solvents that are not as green, that are not as cost efficient, right? So we need to make more progress in the choice of solvents that are used and the different steps that we use. talking about that, since we're removing lignin, then we need to find use for that lignin, right? Because if we don't find use for that lignin, then the cost will be higher. And that would be more or less the concept of biorefinery. We use every molecule that we have in a tree, right? If we remove lignin, we need to find use for lignin as adhesives or others, right? And talking about that, that's why I put this slide here. Last year, we had this Stockholm Declaration of Chemistry for the Future. I suggest that maybe you can come here and see that declaration. It's very good for the professors and the students to reflect, to share, to discuss. It's a beautiful document initially created by Paul Anastas, the father of green chemistry, together with John Warner. And together with a number of people, we signed this declaration in Stockholm. And I invite you to read. But I take these little 4 lines here that you can read that is quite, to me, is quite powerful, right? So it's along the same lines, right? From the context of the environmental impact, but that needs to come side by side with the cost efficiency, because nothing will happen if there is not a proper business model, right? And that's why in the Advancing Technology Readiness program that we have in the Institute, we're looking into this. So we have advisors that do techno-economic assessment, LCA, and all of this. So for the students to do things conscious about the cost and the environmental impact.
Pretty good presentation.
Very simple, but it's just add water and remove water. That's the thing that we need to remember.
So I have 2 questions. One of the questions that I have is in the, I work a little bit on adhesive. So one of the things that I know is that whenever you want to substrate together, there's always this kind of like reaction in terms of could be a cannabis reaction, could be a temperament reaction. When I look at your case, it's a little bit different. So when you have this, you add water and you pick up that water, and then you have these 2 substrates binding together.
Yes.
I just wanted to understand the kind of like force mechanism that will work there.
Well, that will take me to the idea of surface tension that I will briefly explain. That densification that you saw is a self-densification. You don't need to put pressure, actually. You need pressure when you want to put in contact 2 materials that don't talk to each other. But when you have a material like cellulose in front of cellulose, they really love each other, right? And when you have water and you start to remove water, in that condition where you have little water, there will be meniscus of water between the solid fractions, right? And that meniscus has a shape where the curvature is very high. And together with the surface tension forces of water, that is a very high, of all liquids, except mercury, water has the highest surface tension. That's why we're alive. That's because of that. Surface tension of water is very high, 72 millinewtons per meter. That surface tension water, when water is in the form of meniscus between solids, that pulls the solid surfaces to each other by so-called capillary forces, right? And that's how they bind. Those forces are very high. So how to explain this? When you're washing dishes and you put 2 dishes or 2 cover slides together between water, it's very difficult to separate them in the out of plane. Very difficult, right? You need to do like this, right? But that force is capillary forces. That's exactly what we have here. Capillary forces that bring the solids together, and then you have self-densification. And when you remove the water fully, then the material binds very strongly. But the bonding will be a combination. You have mechanical interlocking, you have a bond formation, hydrogen bond, van der Waals forces, all of these add up and make a material that becomes monolithic, interdiffuse into each other, right? So it's a combination of that.
The last question would be like the follow-up. So have you ever looked at the exposure of these material, especially looking at the bottom line, to in moisture? I know that after you take up the water, I expect or I think the material might have a little bit hygroscopic. So in not like exposing it to like water, but just having it like
in humidity environment, in humid environment, 100%. So yeah, that's the problem with cellulose, right? It's hygroscopic material, loves water, and that's a problem. right? We need to prevent that hygroscopicity to take place, right? For that, we play tricks. So we have found that if you add polyvinyl alcohol, if you add chitosan, that's our typical polymers. When you dry the material, the binding is so strong that water cannot really go in, and then you will get something that is water resistant. There is a lot of progress in this area. Cellulose-based foams that are water resistant that you can use in immersion conditions in water. This is possible. And all is that you bind the materials together so strongly that water cannot go in. So you can develop, the short answer is you do develop water resistance if you play with these concepts. It's possible. But pure cellulose will be hygroscopic. That foam that I show, I put it outside, it will absorb water and the properties will change, right? Definitely. But you can go against that by doing chemical modification.
Thank you so much.